My name is Dan Hill. I'm with Canonical. I work in the Sustaining Engineering Department. If I can get my slide to go. There we go. So what is sustaining engineering? We act as a point of escalation for our support teams. We troubleshoot and resolve complex issues, engineer fixes, test and validate the solutions to ensure that they effectively address our customers' needs. We offer Ceph support through Ubuntu Pro. If you're interested in that, please check us out at ubuntu.com/Ceph. Before I start this presentation, I wanted to give credit to Mauricio Oliveira. We had submitted this talk for last year's Cephalicon, and originally conceived the idea as a joint presentation between myself and him, but he was unable to make it to Cephalicon this year. I just want to call him out specifically because he contributed significantly to this presentation, both in terms of the slides, and he was the one who identified root cause and submitted the patch upstream. So where does our journey start? We were engaged to work with a Ceph performance issue. There was a cluster, and I want to start by talking about the Ceph environment. I'm going to be deliberately vague about the cluster specifics, but I wanted to give you a sense of size and scale. The cluster has dozens of nodes, hundreds of OSDs, serving about 10 petabytes of storage, object storage, and they were running on Bionic LTS and running the Octopus version of Ceph. This cluster was being used like a giant ring buffer. They had constant, regular data ingest and constant, regular data expiration with a low level of read activity that varied over time. When we were first engaged, it was to address performance issues, but we quickly noticed that there were several OSDs that were randomly crashing due to checksum errors. With checksum errors, you always suspect that there are hardware issues. We went through, audited the system logs, checked firmware levels, smart data. Everything came back clean. So we started looking for patterns. The checksum errors were spread throughout the cluster on various different types of hardware. And they were happening with a frequency of about 5 crashes across a population of 1,000 OSDs a week. The one pattern that we noticed that was consistent throughout the cluster was that these crashes would only occur during periods of high memory pressure. So we started looking at the Ceph, the checksum error in detail. The first thing that we noticed was that the checksum calculation was pointing to a zeroed buffer. In most cases. So one of the things that we did was we instrumented Ceph so that we would dump the buffer that was being returned. And quickly we noticed two things. In almost all cases, it was a zero buffer that was being returned from the device, and the checksum was failing because it was expecting something else. And then the other thing that we noticed that in some rare instances, at a page boundary, we would see data prior to the page, and then after that page, it would be zeroed. And that was particularly interesting because it pointed at an issue with memory management. The other thing that we noticed was that this is a known issue upstream. We found discussion on transient checksum errors, and there was a mitigation applied to BlueStore, where if a checksum was encountered, it would do a retry, and the retry would usually succeed. But this same kind of retry did not exist in RocksDB. So when RocksDB would read up the data, find the checksum error, it would crash. So one of the early mitigations that we applied was to add that retry to the RocksDB path, so that when direct.io saw this checksum error, we would retry. And we saw the same success. We would see it read this page of zeros, then retry and get the actual data from the device, which is curious. One thing that, since this has to do with memory management, we decided to also try initializing the buffers to a non-zero value, because we were concerned that maybe the data wasn't coming back from the device. But even if we initialize the buffers in Ceph prior to the read to a known non-zero pattern, we would still get all zeros back, which pointed at a memory issue. So alongside Ceph debug, we also tried to recreate this problem internally in our lab environment. We set up a cluster and applied a similar read-write workload to what was seen in the customer's environment. We simulated high levels of memory pressure by running stress-ng, and with this, we were able to reproduce the problem on an average of 3 to 4 days, once every 3 to 4 days, which is painful. Because it's very hard to know with certainty that you haven't encountered the problem if you're trying to assess different fixes. We then took a hard look at the activity that was leading up to the RocksDB checksum errors in our customer's environment, and we realized that there was a critical component missing. I mentioned earlier that they were treating this cluster like a giant ring buffer, and the data expiration was a critical workload that we didn't have in our recreate. So we added a high consistent load of deletes to the cluster, and that reproduced a metadata intensive workload, which brought our recreate time down from once every 3 to 4 days to once every 3 to 4 hours. Which helped us ask questions. Since we now could recreate within hours, we could be more certain that a negative test was a true negative instead of a false negative. So we looked at things like, can we reproduce this issue on more recent kernels or other code levels? In the known issue upstream, it was speculated that there was an issue with swap or a kernel issue that was contributing to this problem. So we tested on the latest mainline kernel, and we still could reproduce the problem. So if the issue was in the kernel, it hasn't been fixed at tip. What was interesting is that we also tested on Focal, which is a later kernel, but also later packages, and we could not reproduce the issue on Focal. So we started looking closely at the delta between Ceph, the Ceph versions. So we eliminated that delta, and we still couldn't reproduce the issue on Focal. And it turns out that there's a change in TCMalloc, there was a later version in Focal that had this commit. So this line, so in TCMalloc, they decided to introduce something called madvice free. And they added a patch in Focal to remove that. So, what is madvice free? This is a system call that hints that when you're freeing the memory, you're hinting to the kernel what it should do with that memory. And there's different constants that you can pass to it. The two that we're particularly interested in here, the ones that are used in TCMalloc, are madvice don't need and madvice free. Madvice don't need indicates to the kernel that the page can be freed right now in line, and the kernel will do that. Madvice free is a lazy free. It's available as a performance optimization. It basically tells the kernel, I don't need this page, and you can free it whenever it's convenient. So it can batch all of these up, free them at a time when it needs to, later down the road. The specific notes here that it can free it at any time. Earlier writes to that same page will cancel the free, and later reads will get a zero-filled page back. The zero-filled page is the key interesting thing here. And this is what led us to realize that this was a kernel issue. So we did have we had two different types of mitigations in place. So RocksDB, we could add retries. The retries would get the correct data from the disk. Or we could have the patch in gperf tools, which changed madvice free to madvice don't need. With don't need, the memory was freed inline, and you didn't have this checksum corruption problem. So this is where we realized it was a kernel issue. We didn't think it was early on, but it ended up being. So what was the problem in the kernel? There are three subsystems that are involved here. You have CPU scheduling, a concurrency issue. You have virtual memory with page table mappings and memory reclaim that occurs when the host is in memory pressure. And then you have this madvice free call and how it is implemented. Then you also have the block IO subsystem, which is using direct IO in this case. So we're going to take a look at the code. This is going to be a very high level. I'm specifically calling out the section in the kernel code that you can review later if you're interested. But I want to call out the key points at where the problem exists. So this is the madvice free implementation. And the key thing to note here is that the dirty page flag is cleared right before it is put onto the LRU, marking the page that it can be freed later. So those sections of code are highlighted there. And then this is the code that tries to unmap the page. So in memory pressure, if the kernel is going into reclaim, it then tries to shrink the page list. So it takes that LRU that has the page, and then it checks to see if I can still unmap it. Because as you recall, the madvice free implementation, if they try to write to the page, then they can no longer unmap it. So the try to unmap call is the key here. Key thing to note here. And then I'll also point out the count VM event. If you're using madvice free, you can then track how many lazy frees are occurring in your environment by looking at the VM stat for PG lazy free. And so this is where the code attempts to unmap. And this is also where the patch gets applied. So the key thing to note here is the page dirty. It checks to see whether or not the page is dirty, and that is the only thing that prevents it from unmapping the page. Okay, and then this is the direct IO, and the thing that I'll note here is that the page is marked dirty only after IO is completed. And so there's a window that exists where the write occurs, but the page has not been dirtied yet. And if the kernel is in memory reclaim, it can then free the page, presenting a zero buffer back to the system. So this is the big picture. It's a very dense slide, but if I kept it in here just to walk through the whole process. Ceph is trying to allocate memory for a direct IO read. The allocation gets interrupted by TCMalloc. TCMalloc requests more memory than it initially needs, and it tries to be friendly with that memory by marking it as madvice free, saying the system can reclaim this because I don't necessarily need it immediately. Ceph requests a direct IO read. Linux starts the direct IO. It hits memory pressure, and then that page can wind up being unmapped. And that's how we hit the problem. So this is a simplified version of the patch. It adds a check to verify the page reference count is the expected page reference count. If it was incremented, then it is not safe to unmap. There's a lot of additional complexity here, but I think that's the simplified explanation of the fix. So. All right, so that's the presentation. Any questions? Yeah. Yeah, if it was buffered, it would not happen. It has to go through the direct I/O. So if you have BlueFS buffered I/O, for example, enabled, that would also prevent this issue.
How long did it take to make all that?
It took, so for the fix to actually land in upstream kernels, it took about 8 to 9 months, I think. But in order for the problem resolution, it took us about a week to come up with mitigations, and then it took us several months in order to actually identify root cause. So.
You mentioned about back in the kernel version 4.5. What's the current status for the strings of several Linux versions?
Yeah, so I have a slide here back up. So these are the backports where we've fixed the kernel versions up in upstream stable kernels, and then I've listed the Ubuntu kernels that have the fix as well. Yeah, yeah, yeah. And then I will also mention, I have this other bonus slide since we're a bit early here. So madvice free in the wild, there have been a number of other open source projects that have encountered issues with madvice free. I've listed some additional links if you're curious about madvice free implementations, using it in your own project, because there's several considerations that you may want to make. Since the kernel is lazy freeing memory, it can cause problems in container environments like in Kubernetes, because an accurate accounting of how much memory is being used cannot happen because the pages are not freed in line. So Go, in particular, implemented this change and then reverted it. TCMalloc, you saw, implemented the change and then reverted it. And this pattern kind of exists in a number of different projects for various different reasons. There's an interesting Facebook talk where they're talking about standard string caching, like improving the speed of standard string. One of the performance improvements that they did was use madvice free, but the fact that you get back this zero page, and that zero page also occurs as a null terminator for a string, caused problems. So they talk about madvice free and how that impacted their ability to cache and quickly manage strings at Facebook. So. Any other questions? Sorry, I couldn't. Oh, TCMalloc? I do not know. So we only looked at TCMalloc. So. Okay. Any other questions? All right. Thank you.